Well, it started out down dirty road. Started out all alone. I'm learning to fly. We ain't got wings. Coming down is the hardest thing. I'm learning to fly around the clouds. What goes up must come down. Hey everybody, welcome to this week's edition of Video Notes for Mr. Flugum's chemistry class. That's right, folks, this is for general chemistry. And these notes will go on page number 48 in your notebook. Alright, and sorry about the title, that's not what we're really talking about. We're talking about gas properties and gas and ideal gases. Well, thanks for tuning in. Let's go ahead and get started. Alright, well let's get started. We're going to talk about something called KMT for short. For long, that is kinetic molecular theory. Okay, so basically this is the idea that all particles in matter are constantly moving. Alright, that's where the kinetic and the molecular comes from. This is a theory, right? Because it helps us explain the way that matter behaves. Alright, and a big part of this is this, you guys. When particle motion increases, that helps explain changes in state. So when particles move fast, are moving somewhat slowly, relatively anyway, they're solid. As they move more, okay, as temperature increases, all right, they turn into a liquid, and when they get really excited and move much faster, it changes into a gas. And so this is how we can kind of understand what's happening at an atomic level with different states of matter. Now today we're going to focus on this right here. We're going to focus on gases and how they behave and how kinetic molecular theory relates to that. So as we talk about this, one thing that is important to remember is this: gases exert pressure. Okay? So that pressure is a result of the collisions between gas molecules and the objects around them. Okay? And that exerts pressure. So I want you to think about this. What factors affect pressure, can affect this pressure? Well, one thing is this, right? The speed of the particles, how fast they're moving, because if they're moving faster, they are going to exert more pressure, right? Because that collision is going to exert more force. Another factor would be this, mass. Okay, so the mass of a particle, when it hits, more massive particles are going to exert more force, right? Okay, another factor is this, is how often, right? How often are these particles colliding with the sides of their container, right? If it's a lot, if it's very often, that's going to be more pressure. If it's not very often, that's going to be very little pressure. Okay, so all of those things are going to contribute to how much pressure is exerted by a gas on its container or the objects around it. Now as we talk about pressure, the base units for pressure are this right here, atmospheres, okay, ATMs, all right, but you'll also see this, you'll also see millimeters of mercury, torr, which these are actually the same thing right here, and you'll also see kilopascals, all right, but the main thing that we're going to work in is atmospheres, all right. So talking about other properties of gases, here's one. Okay, gases can take on any shape or volume. So gases can expand or contract to fit any container, right? If you give them lots of space, they'll fill up all of that space. The particles will expand and put more space between them. You can also compress a gas as well. So we can shrink that space down and the particles will just get closer together. Of course, if you think back to that slide on pressure, this will affect the pressure that a gas exerts, right? Okay. Another thing that is another property of gases is this, right? They act like fluids. So we can pour, they flow, and they move much like liquids do. even though the particles are much farther apart from each other. And also gases have this, they have very low density. Since the particles are far apart, okay, and they're bouncing around, that means that for the amount of space they take up, there's very little mass. Some other gas properties: diffusion. That means gases move easily and mix easily, and they move from high to low concentration. You might notice this, right? If you come into a house where somebody's been cooking, and you'll smell it all over the house, right? But the strongest scent will be in the kitchen where the cooking's happening, right? Okay, so that diffusion means that gas, those smells are moving all throughout from high to low concentration, right? Gases also effuse. So that means this, right? Gases can move through a small pinhole or a small opening in their container and diffuse out and to fill the empty space that is outside. Okay, so now we're going to get into some more theoretical stuff. We're going to talk about something called ideal gases, right? So ideal gases are basically this. They're this gas that doesn't really exist, but we assume that it does because it fits all of the assumptions that we make about gases according to kinetic molecular theory. Now, reality is this though, real gases don't fit this perfectly, especially when they're at high pressure and low temperature, because, well, then weird things happen. But the reason that we use ideal gases is this. It helps us understand the behavior of gases under normal conditions. And this helps us assume this, that all gases act the same, because generally they do at normal conditions, and it allows us to make approximations of a very complex system. There's lots of things that do affect the way that gases move and behave, and when we think of them as an ideal gas, we can take a lot of those variables out and still be pretty accurate with our calculations. Alright, so we have some assumptions about gases. The first is this. Okay, we've got a bunch of tiny particles that are really far apart relative for their size, and because of this idea, that means these particles take up an insignificant volume. So we basically think of gases as being empty space. However, we know this, right? That there's very small particles within that space. However, the volume of the particles is insignificant. Okay, so that's our first assumption. Our second assumption is this, is that when the gas particles run into each other and the container, the collision is elastic. That means there's no energy that's lost, right? So the amount of energy or momentum they have when they hit is equal. If you notice, these arrows are the same size, right? That means that when they hit, boom, they fly apart with the same amount of energy. Now we also know that this isn't true because that's not the way physics works, right? Generally speaking. However, we assume this, all right? Because if the collisions were not completely elastic, then eventually a gas would stop moving. Well, that's not going to happen, folks. Alright, so third thing is real simple. We're assuming that the particles are continuously and rapidly moving. Okay, they're bouncing off each other and objects around them exerting pressure. This is a key fundamental thing about gases. Alright folks, here's our fourth assumption. No forces of attraction or repulsion between gas particles. That means this, they can move easily past each other, right? It's kind of like they really are not bothered one way or the other by the particles around them. Okay, now this is important that we assume this because it takes a whole lot of variables out of our calculations with gases. However, this isn't always true. So there are conditions when these attractions or repulsions between gas molecules become important. And we'll kind of mention those, but for the most part, at regular temperatures and regular pressures around us, there's no attraction or repulsion, or that attraction or repulsion has very, very little impact on how a gas behaves. Alright, so here is the last assumption, alright? Average kinetic energy of a gas depends on the temperature of the gas, right? And remember this, kinetic energy is the energy of motion. Okay, so higher temp means more motion. Okay, so increased temp means increased motion, right? Okay, that is our last assumption. I appreciate you guys tuning in to this presentation and getting these notes. It's going to be very helpful for our last week together. Can you believe it? The school year is almost over. Well, I hope you guys have a great day, and I will see you on Friday. Bye-bye.